something looked older than it should have been. Not broken, not distorted, just formed, structured, heavy with stars. When the first deep-field images from the James Webb Space Telescope arrived in July 2022, astronomers weren't searching for a crisis. They were trying to look farther back than ever before, closer to the first few 100 million years after the Big Bang. The telescope's near-infrared camera was tuned to faint, stretched light that had traveled more than 13 billion years to reach its gold-plated mirrors parked 1.5 million kilometers from Earth at the Sun-Earth L2 point. What Webb detected was expected to be primitive, small, chaotic, just beginning. Instead, some galaxies appeared surprisingly massive, structured and bright at redshifts greater than 10. That places them within roughly 400 to 500 million years after the Big Bang. The anomaly is simple to state. Galaxies in the early universe looked far more evolved than current formation models predicted for that epoch. The first candidates came from Webb's Deep Survey Fields regions like SASMAX 0723 and later the CEERS program. Photometric redshift estimates suggested stellar masses approaching 1010 solar masses at times when the universe was only a few % of its current age. If those measurements held, it meant something fundamental about early galaxy assembly might be incomplete. Not wrong. Incomplete. The instrument wasn't guessing. Webb's infrared sensitivity allows it to detect rest frame optical light shifted into longer wavelengths by cosmic expansion. That light traces older stellar populations, and older stars mean earlier formation. The stakes extend beyond a few distant smudges of light. Galaxy formation is built into the backbone of cosmology. The rate at which dark matter halos grow, the efficiency of star formation, the cooling of primordial gas, all of it connects to how structure emerges from initial density fluctuations measured in the cosmic microwave background. If galaxies grew faster than expected, then either star formation was more efficient, or the first structures collapsed earlier, or the models describing early matter assembly need revision. We are not looking at a small correction. We are looking at a timeline that may have moved. And the shift is measurable. We're about to follow it. The image did not arrive with drama. It appeared on screens in July 2022, sharp, deep, crowded with faint red arcs and distant points of light. The first full-color deep field from the James Webb Space Telescope had been released to the public. Most people saw beauty. Astronomers saw time. Webb was not orbiting Earth. It was stationed nearly 1.5 million kilometers away at the Sun-Earth L2 Lagrange point, a gravitational balance zone where it could keep its sun shield permanently facing the sun. Its 6.5 meters segmented mirror gold-coated beryllium, engineered to detect faint infrared photons, had unfolded months earlier in one of the most delicate deployment sequences ever attempted in space. Infrared light was the reason Webb existed. As the universe expands, light from distant galaxies stretches. Wavelengths grow longer. Ultraviolet becomes visible. Visible becomes infrared. By the time photons from the earliest galaxies reach us, their original signatures have shifted far beyond what the Hubble Space Telescope could reliably detect. Webb was built to see that shift. The first target field centered on the galaxy cluster, SMAX 0723, was not chosen at random. Massive galaxy clusters bend space-time. Their gravity magnifies background galaxies through gravitational lensing, acting as a natural telescope layered on top of Webb's mirror. That meant the instrument could see even farther than its raw aperture might suggest. What astronomers expected in those distant layers was modest. Small protogalaxies, irregular structures, systems still assembling their first substantial stellar populations. According to standard CDN cosmology, structure grows hierarchically. Dark matter halos collapse. Gas falls in. Stars ignite. Over hundreds of millions of years, galaxies merge and grow at redshifts above 10, corresponding to roughly 400 to 500 million years after the Big Bang models predicted galaxies that were dim, compact, and relatively low in stellar mass. Then, Webb's near-infrared camera, NIRCam, began producing catalogues. Objects appeared at photometric redshifts of 10, 11, even 13. That alone was not shocking. The telescope had the sensitivity. What unsettled researchers was brightness. Some candidates appeared too luminous. Brightness in the rest frame optical shifted into infrared wavelengths between roughly 1 and 5 micrometers, suggested substantial stellar mass. Early modeling of several candidates indicated masses approaching 1010 solar masses. For context, the Milky Way today contains on the order of 6 times 1010 solar masses in stars, but it has had 13.8 billion years to build them. These systems had less than 500 million years. The central anomaly can be stated precisely. Galaxies within the first 500 million years of cosmic history appeared significantly more massive and evolved than hierarchical formation models predicted for that time. No one announced a crisis. No one discarded cosmology. But internal discussions shifted. If the redshifts were correct, and if the stellar mass estimates were even roughly accurate, then early star formation must have been more efficient than assumed. Or dark matter halos collapsed earlier, or feedback processes were weaker in the beginning, or the modeling of stellar populations at extreme metallicities required revision within weeks. Independent teams working on the CEER's Cosmic Evolution Early Release Science survey field identified similar high redshift candidates. Preprints began appearing on Arxiv in August and September 2022. Titles were careful, language restrained, unexpectedly massive galaxies, early massive galaxy candidates. The caution was deliberate. Photometric redshift estimation relies on fitting observed flux across multiple filters to template spectra. Breaks in the spectral energy distribution, particularly the Lyman break, indicate where ultraviolet light has been absorbed by intergalactic hydrogen. That break shifts predictably with redshift, but dust can mimic breaks. Active galactic nuclei can distort luminosity. Contamination is always possible. Still, the pattern repeated. Multiple teams, multiple fields, independent reductions. The measurement system itself was sound. NIRCam observes in several infrared bands spanning approximately 0.6 to 5 micrometers. By comparing flux in adjacent filters, astronomers reconstruct a galaxy's spectral energy distribution. The longer the wavelength at which the Lyman break appears, the higher the redshift. Once redshift is estimated, distance and look-back time follow directly from the cosmological expansion history measured by the cosmic microwave background and baryon acoustic oscillations. That expansion history is not speculative. It is tightly constrained, which meant the timeline was fixed. If these galaxies truly existed at redshift 11, they were forming stars when the universe was roughly 3% of its current age. The implications ripple outward. Early galaxy formation influences cosmic reionization, the era when ultraviolet radiation from the first stars ionized neutral hydrogen in intergalactic space. It affects how quickly heavy elements enrich the cosmos. It shapes the growth rate of supermassive black holes observed at redshift 7 and beyond. Change the early galaxy mass function, and you tug on multiple threads. In late 2022, spectroscopic follow-up began using Webb's NIR-SPEC instrument. Spectroscopy measures specific emission lines: oxygen, hydrogen, providing definitive redshift confirmation. Some early photometric candidates were revised downward. Others held. The anomaly narrowed. It did not vanish. By early 2023, confirmed galaxies at redshifts above 10 were no longer theoretical placeholders. They were catalogue entries with coordinates, luminosities, emission line measurements, and error bars. What had started as a beautiful deep field image had become a quantitative tension. Nothing catastrophic, no collapse of cosmology, but a measurable shift in when structure seems to have grown up. So far we know this much: Webb did exactly what it was designed to do. It looked deeper than any telescope before it. It measured stretched light with unprecedented sensitivity. And in that light, galaxies appeared that seemed older than their age allowed. But brightness is not mass, photometry is not spectroscopy, and expectation is not measurement. There is another layer. We need to understand exactly how we measure the age of a galaxy before we decide whether the universe truly matured early, or whether we are misreading its first light. Before we decide whether the universe grew up too quickly, we have to slow down and examine the clock. Astronomers do not measure the age of a distant galaxy the way we date a rock on Earth. No one travels there. No probe returns a sample. Everything begins with light. And light carries two kinds of information at once: distance and history. The key is redshift. In 1929, Edwin Hubble showed that galaxies are receding from us, and that the farther they are, the faster they move away. This recession stretches the wavelength of light. If a galaxy emits ultraviolet radiation at 0.1 micrometers, by the time that light reaches us billions of years later, it may arrive at 1 micrometer or longer deep in the infrared. The stretching factor is called redshift, denoted by Z. If Z equals 10, wavelengths have expanded by a factor of 11. That means the universe has grown 11 times larger since the light was emitted. Redshift is not a guess, it is measurable. When the James Webb Space Telescope observes a faint galaxy, its NIRCam instrument collects photons across multiple infrared filters. Each filter samples a narrow range of wavelengths. Imagine laying colored panes of glass in front of a detector and recording how bright the galaxy appears through each one. Plot brightness against wavelength, and you get a spectral energy distribution. In very distant galaxies, one feature dominates that curve: the Lyman break. Neutral hydrogen absorbs ultraviolet light at wavelengths shorter than 0.0912 micrometers. In young galaxies, that absorption creates a sharp drop in emitted flux below that threshold. If the Lyman break appears in a 1.2 micrometer filter, for example, simple division gives an approximate redshift near 12. This method, photometric redshift estimation, is powerful. It allows researchers to identify thousands of high redshift candidates quickly, but it is not final. Inside a data lab, the process is careful and methodical. Raw pixel arrays arrive from Webb's detectors. Each exposure contains background noise, cosmic ray hits, detector artifacts. Calibration pipelines subtract dark current, correct flat field variations, remove transient spikes. The cleaned images are stacked to improve signal to noise. Then catalogs are generated. Every detected source is measured across filters. Algorithms fit template galaxy spectra based on known stellar population models to the observed flux pattern. The best fitting template yields a probable redshift and a probability distribution around it. It is a statistical exercise grounded in physics. Yet dust complicates things. A dusty galaxy at moderate redshift can mimic the colors of a dust-free galaxy at extreme redshift. Active galactic nuclei can inject extra light at certain wavelengths. Even noise can shift a break by a fraction of a filter width. That is why spectroscopy matters. Webb's InEyeSpec instrument disperses light into a full spectrum. Instead of measuring brightness through broad filters, it spreads photons across thousands of narrow wavelength bins. Emission lines oxygen at 0.507 micrometers, hydrogen alpha at 0.6563 micrometers shift predictably with redshift. When those lines are detected, redshift is no longer inferred from color alone. It is anchored to atomic physics. Several early candidates from 2022 underwent spectroscopic follow-up. Some redshifts were confirmed above Z equals 10. Others were revised downward to Z equals 2020. Others were revised downward to Z That refinement was expected. Science narrows uncertainty, it does not lead to conclusions. Distance, however, is only half the story. The anomaly is about mass. How do we estimate the stellar mass of a galaxy 13 billion light-years away? Again, light is the tool. Young stars shine brightly in ultraviolet. Older stars contribute more strongly to optical wavelengths. By measuring flux in rest frame, optical light shifted into infrared. For high redshift galaxies, astronomers estimate how much stellar material must exist to produce the observed brightness. Population synthesis models simulate how a collection of stars of various masses and ages would emit light. Fit those models to observe spectra, and you infer stellar mass, star formation rate, and approximate stellar age. Here is where tension entered the picture. At redshifts above 10, the universe was less than 500 million years old. That places strict limits on how long stars could have been forming. If a galaxy appears to contain 10 solar masses in stars, then either it formed stars at an extraordinary rate, hundreds of solar masses per year sustained over hundreds of millions of years, or the mass estimate is inflated. Neither explanation is impossible. Both require careful examination. The timeline itself comes from the cosmological model calibrated by observations of the cosmic microwave background, particularly from missions like Planck Space Observatory. Planck measured temperature fluctuations at redshift 1100, constraining the universe's expansion history and age to about 13.8 billion years with percent-level precision. That means look-back time for a given redshift is not flexible by billions of years. At Z equals 10, the universe truly was young. So far we know. Redshift measurement techniques are robust when spectroscopically confirmed. Stellar mass estimation relies on well-tested population models, but becomes more uncertain at extreme distances and low metallicities. The timeline is anchored by independent cosmological probes. The anomaly sits at the intersection of these methods. Either early galaxies form stars faster and more efficiently than predicted, or our interpretation of their light is incomplete. But before we question interpretation, we need to understand what theory expected in the first place. Because there is another layer. The models themselves have a history and assumptions built into them. Before Webb ever unfolded its mirror, the early universe had already been mapped, at least in simulation. Not visually, not photographically, but mathematically. The standard framework is called lambda cold dark matter, or THETM. It is not a loose idea, it is a model, constrained by precise measurements of the cosmic microwave background, large-scale galaxy surveys, baryon acoustic oscillations, and supernova distances. Together, these observations describe a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Structure formation begins with tiny density fluctuations. Variations in matter density measured to 1 part in 100,000 in the cosmic microwave background by missions like Planck Space Observatory. Those fluctuations are the seeds. Dark matter, which does not emit or absorb light, responds only to gravity. Over time, slightly denser regions pull in more matter. Small clumps collapse first, larger structures build gradually through mergers. This is called hierarchical growth. In this picture, the earliest galaxies are small because the dark matter halos that host them are small. Simulations such as Illustris, EAGL, and later hydrodynamic models track this process numerically. They begin shortly after recombination and evolve forward through billions of years. The equations include gravity, gas cooling, star formation recipes, supernova feedback, black hole growth, and radiation effects. By redshift 10, roughly 470 million years after the Big Bang models predicted that dark matter halos above about 10 solar masses would be rare. Most halos would be closer to 10 Tate or 10 solar masses. Since only a fraction of halo mass converts into stars, stellar masses were expected to be significantly lower. In practical terms, galaxies at that epoch were predicted to contain perhaps 10⁷ to 10⁸ solar masses of stars. bright systems might push higher, but sustained star formation at extreme rates was thought to be limited by feedback. Feedback is critical. When massive stars explode as supernovae, they inject energy into surrounding gas. That energy heats and expels material, slowing further star formation. Early galaxies with shallow gravitational wells were expected to lose gas easily. That suppresses runaway growth. This expectation shaped observational strategy. When the James Webb Space Telescope was designed, it was meant to detect faint proto-galaxies assembling slowly. It would study the transition from population 3, stars the first generation formed from pristine hydrogen and helium, to chemically enriched galaxies. No one predicted an absence of structure, but the predicted number density of massive galaxies at ZE10 was low. Then came the early Webb catalogues. Some analyses suggested galaxies with stellar masses approaching 10 solar masses at redshift 10 or higher. If correct, that implied dark matter halos, perhaps 10-11 solar masses or more, existing within the first half-billion years. Simulations did not entirely forbid such halos, but they were statistically rare. When researchers compared observed number densities to theoretical halo mass functions, tension emerged. Some early estimates suggested the abundance of massive galaxies could be an order of magnitude higher than predicted. Not infinite, not infinite, not impossible, but higher. Theoretical cosmology is not fragile. It tolerates adjustments, but parameters are interconnected. Increase early halo abundance significantly, and you risk conflicting with cosmic microwave background constraints or later large-scale structure observations. That is why caution followed excitement. Were stellar masses overestimated? Early spectral energy distribution fits assumed particular star formation histories, often constant or smoothly rising rates. If instead these galaxies experienced short, intense bursts, the inferred mass-to-light ratio might be different. Metallicity matters too. Early stars contained almost no heavy elements. Metal-poor stellar populations emit light differently than enriched ones. If models underestimate how luminous metal-poor stars are, then mass estimates could be biased high. The anomaly sharpened into a question: are the models missing an efficiency mechanism? Or are the observations misinterpreting brightness as maturity? So far we know this much. First M predicts gradual growth of structure through hierarchical merging of dark matter halos. Feedback processes regulate star formation. Massive galaxies at extreme redshift are not forbidden, but they are expected to be rare. Webb's early observations suggested they might be more common than anticipated, but models are layered. Dark matter growth is one component. Gas cooling physics is another. Star formation efficiency, feedback strength, black hole activity, all shape outcomes, and dark matter halos themselves form according to statistical distributions governed by initial density fluctuations. If we want to understand whether galaxies grew up too fast, we need to look at the scaffolding beneath them. Because there is another layer, the invisible framework that allowed any galaxy to exist at all. Galaxies do not begin with stars. They begin with gravity. Long before hydrogen clouds cooled enough to ignite fusion, something invisible was already gathering mass. Dark matter, non-luminous, collisionless and detectable only through gravitational effects, collapsed first. Without it, galaxies would not form. In the THIT-CDM framework, dark matter makes up roughly 85% of the universe's total matter content. Its particles, whatever their true nature, move slowly compared to the speed of light. That cold behavior allows small-scale structures to grow early. Tiny density fluctuations expand under gravity, regions slightly denser than average pull in surrounding matter, deepening potential wells. The mathematics of this growth is encoded in what cosmologists call the halo mass function. At any given redshift, The halo mass function predicts how many dark matter halos exist per unit volume at a given mass. It is derived from the initial fluctuation spectrum measured in the cosmic microwave background, and evolved forward using gravitational collapse theory. At redshift 0, the present-day massive halos above 1014 solar masses host galaxy clusters. At redshift 10, the distribution shifts dramatically. The universe was smaller, denser, and only a few 100 million years old. There had been less time for small halos to merge into larger ones. Most halos at redshift 10 were expected to fall between 10.8 and 10.9 solar masses. Halos above 1011 solar masses were statistically rare, not impossible, but rare. If a galaxy appears to contain 1010 solar masses in stars, then its host halo must be substantially more massive. Only a fraction of halo mass converts into stars, typically a few percent at most, depending on redshift and feedback processes. So when early Webb data suggested unexpectedly massive galaxies, cosmologists immediately examined whether such halos could plausibly exist in sufficient numbers. The question is quantitative. Using Press-Schechter theory and its refinements, researchers calculate the expected number density of halos at a given mass and redshift. These calculations depend sensitively on the amplitude of initial density fluctuations, parameterized by CUH, and the matter density of the universe, both tightly constrained by missions like Planck's Space Observatory. Planck's measurements limit how much freedom there is to increase early halo abundance without disrupting the fit to the microwave background. If you try to dramatically boost halo growth at early times, you risk altering the pattern of temperature anisotropies observed at redshift 1100. That constraint acts like a boundary. When researchers compared Webb candidate galaxies to predicted halo distributions, some early analyses suggested tension at the high mass end. The number density of bright, massive candidates at Z10 appeared higher than many simulations had anticipated. But halo formation is not purely deterministic. Rare peaks in the density field can collapse earlier than average. These are statistical outliers, regions that were slightly denser than their surroundings in the primordial fluctuation map. In large survey volumes, rare peaks are expected. The challenge lies in abundance. If Webb observes more massive early galaxies than rare peaks can account for, then either survey volumes are sampling unusual regions or assumptions about star formation efficiency within halos need revision. There is also the question of halo concentration and gas accretion rates. At early times, gas densities were higher. Cooling times were shorter in dense regions. Cold streams of gas could flow efficiently into halos without being shock heated, particularly below a critical halo mass threshold. That might accelerate star formation under certain conditions. Hydrodynamic simulations have begun exploring these possibilities. Yet none of this overturns gravity itself. The growth rate of dark matter halos follows from general relativity and the measured expansion history. You cannot arbitrarily speed it up without altering the cosmological model in ways that ripple outward. So far we know, dark matter halos provide the gravitational scaffolding for galaxy formation. Their abundance at redshift 10 is tightly constrained by initial density fluctuations measured independently. Massive halos at that epoch are rare but not forbidden. The anomaly arises if observed galaxies require more massive halos or more numerous massive halos than predicted. But halo mass alone does not determine stellar mass. Even in a large halo, star formation can be inefficient. Gas must cool. Stars must ignite. Feedback must not expel too much material, which means the next layer lies not in gravity alone, but in how efficiently early galaxies converted gas into stars. Because if halos were present in sufficient numbers, then perhaps the real surprise is not when gravity assembled mass, but how quickly baryonic matter turned that mass into light. Gravity builds the frame. Gas builds the light. Dark matter halos can exist without shining. They are scaffolds. What makes a galaxy visible is how efficiently ordinary matter hydrogen and helium collapses, cools, and ignites into stars inside those halos. The anomaly we are tracing depends heavily on one parameter: star formation efficiency. In simple terms, this is the fraction of available gas that turns into stars over time. In the nearby universe, that fraction is modest. Only a small percentage of a galaxy's baryonic mass becomes stellar mass. Supernova explosions heat surrounding gas. Stellar winds push material outward. Radiation pressure disrupts dense clouds. Feedback regulates growth. Early galaxies were expected to be even more fragile. At redshift 10, halos were smaller. Their gravitational wells were shallower. When the first massive stars exploded, models suggested they would expel gas efficiently, slowing further star formation. This self-regulation keeps galaxies from growing too quickly. But Webb's early observations suggested brightness levels that implied rapid stellar mass buildup. To sustain 1010 solar masses in stars within 400–500 million years, a galaxy would need average star formation rates of tens to hundreds of solar masses per year, sustained over a large fraction of that period. That is not impossible, but it is intense. One explanation involves the physical conditions of early gas. The first generations of stars formed from metal-poor gas. Metals elements heavier than helium act as cooling agents in interstellar clouds. In their absence, gas cools differently. Some theoretical models suggest that metal-poor gas can collapse into massive stars more readily under certain densities. Population third stars. The first stars were likely massive and short-lived. They produced heavy elements through supernova explosions, enriching surrounding gas. After a few generations, galaxies would contain enough metals to alter cooling pathways. If metal-poor stellar populations are more luminous per unit mass than previously modeled, then brightness might not translate directly to extreme stellar mass. That would reduce tension. Another factor is gas inflow. In the early universe, cosmic gas densities were higher. Simulations show that cold streams of gas can penetrate halos efficiently at high redshift, feeding central regions without being shock heated to high temperatures. Continuous cold accretion could sustain high star formation rates longer than once assumed. There is also the question of feedback strength. Most galaxy formation models include parameterized feedback recipes. These are not arbitrary, but they are tuned to reproduce observations at later cosmic times. If feedback was weaker in the earliest galaxies, perhaps due to different interstellar medium conditions, then star formation might proceed more aggressively before regulation sets in. A scene helps clarify this. Imagine a simulation running on a supercomputer cluster. The volume represents a cubic region of early universe space. Dark matter particles move under gravity. Gas elements flow into forming halos. At each time step, the code evaluates density thresholds. If gas exceeds a certain density and temperature condition, star formation is triggered according to a prescribed efficiency parameter. That parameter is not measured directly. It is inferred from matching simulations to observed galaxies at lower redshifts. Small changes to that efficiency factor can produce large differences in early stellar mass buildup. Some recent theoretical work has explored the possibility that early star formation efficiency approached 10% or higher in certain halos, significantly above conventional assumptions for that epoch. If true, galaxies could accumulate stellar mass more rapidly without requiring an overhaul of dark matter halo growth. Yet even this explanation faces limits. Gas supply is finite. Sustained star formation at extreme rates requires continuous accretion. Feedback, even if weaker, cannot vanish entirely. Supernova energy deposition is governed by physics, not preference. So far we know, dark matter halos at redshift 10 are rare but plausible at high masses. To explain unexpectedly bright early galaxies, either star formation efficiency must have been higher than many models assumed, or stellar population properties differ from expectations, brightness does not equal maturity in a simple way. But we cannot fully trust brightness alone. Infrared observations can be influenced by dust. Emission from active galactic nuclei can inflate luminosity estimates. Even template mismatches in spectral energy distribution fitting can bias mass calculations. Which means there is another layer. Before rewriting star formation physics, we must examine whether we are misinterpreting the light itself. Brightness feels decisive. A galaxy either shines strongly or it does not, but in the infrared, brightness can hide complications. When the James Webb Space Telescope began delivering deep-field images, early mass estimates depended heavily on spectral energy distribution fitting. Photometry across multiple NIRCam filters was compared to model galaxy templates. From that fit came redshift probability, stellar mass, star formation rate, and age. But templates are not reality. They are approximations built from known stellar populations, dust attenuation laws, and assumed star formation histories. At redshifts beyond 10, we are fitting models to systems unlike anything directly observed before. Dust is one of the most persistent uncertainties. Interstellar dust absorbs and scatters ultraviolet and optical light, then re-emits it at longer wavelengths. A dusty galaxy at moderate redshift can appear red in color, similar to a dust-free galaxy at extreme redshift. In photometric surveys, this degeneracy matters. If a galaxy's redness is caused by dust rather than cosmic expansion, its true redshift could be lower than initially estimated. Early Webb analyses accounted for this possibility. Teams tested alternate fits that allowed for dusty, lower redshift solutions. In some cases, high redshift candidates were indeed reclassified after deeper data or spectroscopic follow-up, but not all of them. Spectroscopy helps break degeneracies. When Webb's NISPEC instrument detects emission lines such as OR3 or hydrogen bomber lines, the redshift becomes anchored to atomic transitions rather than color breaks alone. Several high redshift candidates survive spectroscopic scrutiny. Still, mass estimation carries additional uncertainty. Stellar mass-to-light ratios depend strongly on assumed star formation histories. If a galaxy formed most of its stars in a brief, intense burst shortly before observation, its light would be dominated by young, luminous stars. That can inflate brightness relative to mass. Conversely, if older stellar populations contribute significantly, then the galaxy may contain more mass than its ultraviolet light suggests. Metallicity adds complexity. Early galaxies likely contained lower heavy element abundances than nearby systems. Metal-poor stars could be bluer and more luminous at certain wavelengths. If models underestimate this effect, inferred stellar masses could be biased. There is also the possibility of active galactic nuclei. Supermassive black holes accreting material emit intense radiation across multiple wavelengths. Even a modestly active nucleus can contribute significant infrared luminosity. If not properly accounted for, that emission can mimic a massive stellar population. In some early Webb candidates, researchers search for AGN signatures, broad emission lines, high ionization states, or X-ray counterparts. In most cases, clear AGN indicators were absent, but faint or obscured activity cannot always be ruled out. By late 2023, revised mass estimates began appearing in follow-up papers. Some early 1010 solar mass claims were adjusted downward by factors of 2 or more. Improved modeling of star formation histories and nebular emission lines reduced tension in several cases. The anomaly narrowed again. Yet even after revisions, the numbered density of relatively massive galaxies at redshifts above 10 remained higher than many pre-Webb models had predicted. The pattern did not disappear. So far we know, dust and template degeneracies can inflate redshift and mass estimates. Spectroscopy corrects some early overestimations. Improved modeling reduces extreme outliers. but confirmed galaxies at very high redshift remain more luminous and more abundant than many simulations anticipated. The light is not pure illusion. The question shifts from whether the anomaly exists to how large it truly is. If brightness is not entirely misleading, then spectroscopic confirmation becomes critical, because color breaks suggest distance, but emission lines prove it, and once distance is proven, the timeline becomes fixed. There is another layer waiting in those spectral lines. Color can suggest distance. Spectral lines confirm it. After the first wave of photometric candidates emerged from Norcaminga imaging, attention shifted to Webb spectrograph NICE-SPEC. Unlike broadband imaging, spectroscopy spreads incoming light into a detailed spectrum. Instead of measuring brightness in a handful of filters, NICE-SPEC records flux as a continuous function of wavelength. If a galaxy truly sits at redshift 10 or beyond, specific atomic fingerprints must appear at precise shifted positions. Hydrogen emission lines, oxygen doublets, neon transitions. Atomic physics does not bend to interpretation. In late 2022 and through 2023, Webb began confirming redshifts spectroscopically for selected high-priority candidates. In several cases, emission lines appeared exactly where high redshift models predicted. Galaxies were confirmed at redshifts above 10 some approaching Z, 12 and beyond. That corresponds to light emitted roughly 350 to 400 million years after the Big Bang. At that point, the anomaly became anchored in measurement. Spectroscopic confirmation eliminates the possibility that these systems are dusty interlopers of moderate redshift. It fixes their position in cosmic time, the expansion history, calibrated by the cosmic microwave background and large-scale structure surveys, determines their look-back time precisely once redshift is known. What spectroscopy does not directly measure is stellar mass. It confirms distance. It detects emission lines that indicate star-forming regions. It can constrain metallicity and ionization conditions, but stellar mass still relies on modeling the continuum like the integrated glow of stars across wavelengths. Even so, spectroscopy strengthened the case that early galaxy formation was occurring earlier and more vigorously than expected. In some confirmed systems, emission line strengths indicated intense star formation rates. High equivalent widths of 4 and hydrogen lines suggested compact, energetic regions dominated by young stellar populations. These galaxies were not quiet, they were active. One confirmed galaxy, observed less than 400 million years after the Big Bang, showed clear oxygen emission lines shifted into infrared wavelengths detectable only with Webb's sensitivity. That oxygen must have been produced by previous generations of stars, meaning star formation had already been underway long enough to enrich the interstellar medium. The timeline compresses. If a galaxy at redshift 12 already contains measurable heavy elements, then star formation must have begun even earlier, perhaps at redshift 15 or higher. That pushes the onset of significant stellar activity closer to 250 to 300 million years after the Big Bang. So far we know some early photometric overestimates were corrected, but several high redshift galaxies have been spectroscopically confirmed. Their existence at extreme early times is not speculative. The anomaly now shifts from "are they really distant?" to "how did they assemble so quickly?" Spectroscopy also revealed something subtle. Line widths and profiles sometimes suggested turbulent internal conditions, high gas densities, strong radiation fields. These are environments capable of rapid star formation under the right circumstances. But spectroscopy alone does not rewrite cosmology. The confirmed number of massive galaxies remains small in absolute terms. Survey volumes are limited. Cosmic variance, the statistical fluctuation in galaxy density across different regions, can exaggerate apparent abundance. To determine whether this is a true global tension, astronomers need larger samples, deeper surveys, and careful modeling of observational biases. Still, the fact remains, Galaxies existed in structured, chemically enriched states earlier than many simulations anticipated. Dark matter halos were present. Star formation was active. Heavy elements were already circulating. The universe did not wait quietly. But before adjusting cosmological parameters or rewriting feedback models, we have to examine something less visible: the assumptions built into simulations themselves. Because there is another layer not in the sky but in the code. The sky does not contain parameters. Simulations do. When cosmologists model the early universe, they begin with equations grounded in gravity and thermodynamics. But galaxies are complex systems. Not every physical process can be resolved directly. Many occur on scales far smaller than computational grids allow. So researchers build prescriptions, star formation recipes, feedback efficiencies, gas cooling thresholds, black hole accretion models. Each is based on observation and theory. Each contains assumptions. When a simulation tracks gas collapsing inside a dark matter halo, it cannot follow every individual star-forming cloud. Instead, once gas density exceeds a chosen threshold and temperature falls below a defined limit, the code converts a fraction of that gas into stellar particles according to a star formation efficiency parameter. That parameter is calibrated. Often it is tuned so that simulations reproduce observed galaxy populations at redshift 0 or 2 epochs where data are abundant. But the early universe was different. Lower metallicity, higher gas density, stronger background radiation fields, rapid halo assembly. The question is whether recipes tuned for later epochs remain accurate at redshift 10 and beyond. Even small shifts in assumptions can produce significant changes in early stellar mass buildup. Consider feedback strength. Supernova feedback is typically implemented by injecting thermal or kinetic energy into surrounding gas cells. The efficiency of that energy coupling determines how much gas is expelled from the halo. If feedback is slightly weaker in early conditions, perhaps because cooling times differ, then star formation could proceed more rapidly before self-regulation takes hold. Alternatively, consider star formation thresholds. If the density threshold for star formation is set too high relative to early gas conditions, simulations may artificially delay star formation. Lowering that threshold in high redshift environments can increase early stellar mass. None of these adjustments violate physics. They refine how unresolved processes are represented. There is also resolution. Simulations must choose between large cosmological volumes and fine spatial detail. Large volumes capture rare massive halos statistically. High resolution captures small-scale gas physics more accurately. Few simulations can achieve both simultaneously. If early massive galaxies are rare, large volumes are needed to sample them. If early star formation physics is sensitive to small-scale turbulence, high resolution is critical. The tension between these demands shapes results. When Webb's early data appeared, several groups revisited simulation outputs. Some found that within statistical uncertainty, rare high-mass halos could account for observed candidates. Others suggested that modest increases in star formation efficiency at high redshift could reconcile predictions with observations without altering Thunt-8 CDM parameters. Importantly, no widely accepted analysis required abandoning the standard cosmological framework. The anomaly resides within galaxy formation physics, not necessarily in dark energy, dark matter, or expansion history. That distinction matters. So far we know, simulations contain parameterized recipes for star formation and feedback. These are calibrated primarily against later epoch observations. Early universe conditions may justify adjustments. Small parameter shifts can significantly alter predicted stellar mass at redshift 10. The anomaly may reflect incomplete modeling rather than flawed cosmology. But modeling choices are only part of the measurement chain. We also need to understand how observational pipelines translate photons into catalog entries. Detector calibration, noise filtering, flux extractional influence derived properties, because if we are adjusting theory, we must be certain the measurement infrastructure is sound. There is another layer. It lies in the instruments, the data pipelines, and the global network that transforms faint infrared light into numbers. Before a galaxy becomes a data point, it is a faint signal buried in noise. The James Webb Space Telescope does not send back finished images. It transmits streams of raw detector counts arrays of numbers representing electrons released when infrared photons strike sensor pixels. Those counts must be calibrated, corrected, aligned, and interpreted. The integrity of this pipeline matters as much as the telescope itself. Webb's primary imager, NIRCam, operates between roughly 0.6 and 5 micrometers. Its detectors are sensitive enough to measure flux from galaxies with apparent magnitudes fainter than 30 in deep exposures. At those levels, background subtraction becomes delicate. Thermal noise from the telescope, zodiacal light from interplanetary dust, and cosmic ray hits all contaminate raw data. Inside the Space Telescope Science Institute in Baltimore, calibration teams built layered correction pipelines long before launch. Each exposure undergoes dark current subtraction, flat field correction, detector nonlinearity adjustment, and cosmic ray flagging. Dithered exposures are aligned and combined to improve signal to noise. Only after this reduction process does source extraction begin. Software identifies clusters of pixels above background thresholds. Photometry measures total flux in each filter using carefully defined apertures or model-based fitting. Every measurement includes uncertainty estimates, photon noise, background variance, detector systematics. Redshift estimation follows. Photometric redshift codes compare observed fluxes to thousands of template spectra. These templates span ranges of metallicity, dust attenuation, and star formation history. For each galaxy, the algorithm produces a probability distribution function across redshift space. If the probability peaks sharply at Zinj, in need 11, with little weight at lower redshift solutions, confidence increases. If the distribution is broad or bimodal, caution remains. Once photometric candidates are identified, spectroscopic follow-up with NISPEC provides confirmation where possible. NISPEC uses micro-shutter arrays, tiny individually controllable shutters, to isolate multiple galaxies simultaneously. Light passes through dispersive elements that separate wavelengths into fine bins. Emission lines appear as sharp peaks. Those lines are measured, fitted, and converted into redshift values with well-defined uncertainties. Instrument calibration ensures wavelength solutions are accurate to within fractions of a nanometer. None of this is casual. Webb's detectors were characterized extensively before launch. In-flight calibration programs regularly monitor sensitivity drift, background levels, and instrument stability. Independent research teams process the same datasets with separate pipelines to cross-check results. The anomaly we are tracing does not arise from a single group or a single reduction method. It emerges from multiple surveys, early release science programs, the CERS field, lensing cluster observations. Independent teams using different photometric fitting codes reached similar conclusions, though with varying mass estimates and confidence levels. Cosmic variance remains a factor. Deep surveys cover small sky areas. The universe is not uniform at small scales. A survey pointed toward a region slightly richer in early massive halos could skew early interpretations. To address this, astronomers expand survey footprints over time. Additional fields reduce statistical bias. So far we know the measurement infrastructure behind Webb is robust. Data reduction pipelines are carefully calibrated. Spectroscopic confirmation anchors redshift measurements. Independent teams reproduce key findings. The anomaly is not the product of a single flawed dataset. It arises from cumulative evidence that some galaxies assembled significant stellar mass earlier than many simulations predicted. Yet even with improved data and modeling refinements, a subtle tension remains in certain analyses. The number density of relatively massive galaxies at extreme redshift may be higher than anticipated. To understand whether that tension persists, we must isolate exactly what current models still struggle to explain. There is another layer. It lies in the residual gap between prediction and observation, small but measurable. By the end of 2023, the early shock had softened. Mass estimates were revised. Some extreme claims were moderated. Spectroscopy clarified distances. Simulations were rerun with adjusted parameters. And yet, a quiet tension remained. Not a collapse of CDM, not a contraction of the cosmic microwave background, something narrower. The number density of luminous galaxies at redshift above 10 still appeared in several analyses, somewhat higher than many pre-Webb simulations had forecast. The difference was not orders of magnitude across the board. It was concentrated at the bright, high-mass end of the distribution. In hierarchical structure formation, rare massive halos correspond to rare peaks in the primordial density field. The abundance of those peaks falls steeply with mass. That steep decline is what makes extremely massive early galaxies statistically uncommon. But Webb's surveys began identifying more candidates in that high luminosity regime than expected under typical star formation efficiency assumptions. The key word is typical. Simulations do not predict a single outcome. They produce distributions based on parameter choices. Many pre-Webb galaxy formation models assume star formation efficiencies and feedback strengths calibrated to match galaxies at redshift 2.6. When extrapolated to redshift 10 to 12, these models tended to yield fewer massive systems than Webb's early counts suggested. When researchers adjusted star formation efficiency upward within plausible bounds, tension decreased. But in some cases, doing so risked overproducing galaxies at slightly later epochs. The challenge is consistency across time. A model that explains C-squared 10 observations must also match galaxy counts at C-squared 6, 4, and 2, and ultimately align with present-day galaxy distributions. Increasing early efficiency cannot distort the full cosmic evolution curve. Another area of tension lies in stellar mass estimation. Even after revisions, some confirmed high redshift galaxies show spectral energy distributions consistent with substantial stellar mass already in place. The presence of measurable oxygen emission lines implies prior generations of star formation, meaning enrichment happened quickly. Chemical enrichment timescales become compressed. To produce oxygen, massive stars must form and explode as supernovae. That cycle takes only a few million years, but assembling significant metal content across a galaxy requires sustained activity. In simulations, enrichment occurs naturally, but reproducing observed metallicities at extreme redshift may require efficient mixing and rapid recycling of gas. There is also the matter of reionization. The universe transitioned from neutral to ionized hydrogen between redshifts roughly 6 and 10. Galaxies are thought to be the primary drivers of that process. If early galaxies are more numerous or more efficient at producing ionizing photons than predicted, reionization models may need adjustment. However, current reionization constraints from quasar absorption spectra and cosmic microwave background polarization still fall within ranges compatible with Webb's emerging data. So far we know, models can accommodate earlier and more efficient galaxy formation without abandoning the core cosmological framework, but doing so requires careful recalibration to maintain consistency across cosmic history. The residual anomaly is subtle. Early galaxies appear to have assembled stellar mass somewhat faster and perhaps somewhat more abundantly than many models anticipated. It is not a contradiction, it is a parameter tension. And parameter tensions are often where refinement begins. But refinement does not move in one direction only. Alternative interpretations remain under active discussion. Stellar masses may still be overestimated in some cases. Nebula emission line contamination can bias photometric fits. Stellar population models at extremely low metallicity are still improving. There is not one explanation. There are competing interpretations, and before projecting forward we have to examine them side by side, because there is another layer, not of data, but of interpretation. When a signal sits at the edge of what we can measure, multiple explanations can survive at once. That is where this story lives. Webb's early data revealed galaxies that appeared bright and substantial at redshifts above 10. Some were spectroscopically confirmed. The timeline was fixed, but the meaning of that brightness, how much stellar mass it implies, how fast it formed, and what it says about early structure remains under debate. The interpretations cluster into a few main paths. 1. They really are massive, and the early universe was efficient. In this view, the simplest explanation is also the most direct. Early galaxies formed stars at higher efficiencies than many simulations assumed. Gas accreted rapidly through cold streams. Feedback was present but did not suppress growth as strongly in the first few 100 million years. Stellar mass built quickly. This interpretation does not require new physics. It requires earlier, faster assembly within that CDM. The price is calibration. If high efficiencies are common at ZD10, models must still match galaxy populations at later times without overshooting. That means early rapid growth may need to taper quickly or be restricted to rare environments. 2. They are less massive than they look because light is being boosted. Here the focus shifts to mass-to-light ratios. At extreme redshifts, the light we observe is dominated by young hot stars and by nebular emission from ionized gas. Strong emission lines can fall inside certain near-cam filters, artificially boosting measured flux. If that extra flux is interpreted as stellar continuum, the inferred mass can be too high. This effect is real and measurable. It is one reason some early mass estimates were revised downward. If the emission line boosting is stronger than initial fits assumed, many massive galaxies might actually be lighter, just extremely active. That would reduce the anomaly without requiring major changes in formation timelines. 3. Some candidates are contaminated by dust or low redshift interlopers. Even with careful fitting, photometric redshift catalogs can include contaminants. Dusty galaxies at moderate redshift can mimic high redshift colors. A small fraction of misclassifications can inflate apparent number counts at Zen 10, especially because true high redshift galaxies are rare. Spectroscopy removes this uncertainty for confirmed objects, but many candidates remain unconfirmed due to faintness. This interpretation suggests the anomaly is partly statistical. Early surveys overcounted, and future larger samples will settle closer to predicted abundances. 4. Black hole activity is contributing to the light. A growing black hole can emit radiation that alters a galaxy's spectral energy distribution. Even without obvious AGN signatures, faint accretion could contribute infrared light or modify continuum shapes. This explanation is difficult to test in every case, but it remains on the table, especially for unusually luminous objects. If some confirmed high redshift galaxies contain actively accreting black holes, their luminosity might be inflated relative to stellar mass. 5. Stellar population models are incomplete at very low metallicity. This is quieter but important. Stellar evolution models are calibrated using nearby stars at extremely low metallicity conditions closer to the first few 100 million years stellar lifetimes. Spectra and mass-to-light relationships may differ subtly. If early stellar populations are intrinsically more luminous than assumed, mass estimates derived from light could be biased high. This would again reduce tension without changing halo growth. So far we know, multiple interpretations remain plausible. Spectroscopy confirmed that some galaxies truly exist at extreme redshift, so distance is not the main uncertainty. The remaining debate focuses on stellar mass inference, emission line contamination, and the underlying efficiency of early star formation. The anomaly persists as a measurable tension, but its magnitude depends on which interpretation dominates. What happens next is not a single decisive experiment. It is accumulation, more spectra, larger survey areas, better modelling, cross-checks with other instruments and future missions. And that leads naturally to the future, because the next stage of this investigation is not about what Webb already saw. It is about what Webb will see when the sample grows large enough that rare outliers become a statistical pattern. There is another layer ahead. Early Webb data felt concentrated. Small fields, deep exposures, a handful of surprising candidates. That is how anomalies begin inside limited volumes. But cosmology does not rest on handfuls. To determine whether early massive galaxies are rare exceptions or a genuine shift in formation timelines, the sample must grow. The James Webb Space Telescope was designed for longevity. Its cryogenic systems and stable orbit at L2 allow years of deep field observation. Each new observing cycle expands both depth and area. Depth reveals fainter galaxies. Area reduces cosmic variance. Several ongoing survey programs are systematically mapping larger sky regions at high sensitivity. Instead of focusing on single gravitational lensing clusters, astronomers are targeting blank fields to measure unbiased galaxy number densities at redshifts above 8, 10, and even 12. The statistical question is precise. How many galaxies above a given stellar mass exist per cubic megaparsec at a given redshift? That number, known as the stellar mass function, can be directly compared to theoretical predictions. If early survey fields happen to sample overdense regions, later wide field observations should show lower average abundances. If not, and high mass systems remain common across multiple regions, models must adjust accordingly. Spectroscopic campaigns are also scaling up. NIRSpec's multi-object capabilities allow dozens of faint galaxies to be observed simultaneously. Each confirmed redshift tightens the high redshift census. Emission line strengths refine star formation rate estimates. Line ratios constrain metallicity and ionization conditions. With larger datasets, uncertainties shrink. Another instrument, the Mid-Infrared Instrument, MII, aboard Webb, extends observations to longer wavelengths. This allows better constraints on dust emission and stellar population ages. If dust contamination is significant, mid-infrared data will reveal it more clearly. Beyond Webb, future missions will widen the picture. The upcoming Nancy Grace Roman Space Telescope will survey much larger sky areas in infrared wavelengths, though at shallower depth than Webb's deepest fields. Roman's wide-field imaging will improve constraints on the abundance of bright high-redshift galaxies across cosmic volume. Ground-based observatories also contribute. 30-meter-class telescopes under construction will provide high-resolution spectroscopy for faint early galaxies, measuring kinematics and chemical abundances with greater precision. So far we know, current Webb observations suggest some early galaxies assembled substantial stellar mass sooner than many simulations anticipated. The magnitude of that tension depends on sample size, stellar mass modeling, and cosmic variance. Future surveys will test whether these galaxies are statistical outliers or indicators of systematically earlier growth. If larger datasets confirm elevated number densities at the high mass end, simulations will need recalibration, likely within galaxy formation physics rather than fundamental cosmology. If numbers converge downward with broader sampling, the anomaly may resolve into statistical fluctuation combined with early modeling overestimates. Either way, the answer will be quantitative. No single galaxy decides the case. It is the distribution that matters. And that distribution feeds directly into the next layer of cosmic history, because if galaxies truly formed earlier and faster, then the timeline of reionization, chemical enrichment, and black hole growth may also shift. The ripple moves outward. There is another layer. It connects these early structures to the broader arc of cosmic evolution. When galaxies form earlier, everything downstream feels it. Structure in the universe is not isolated. Dark matter halos, stars, black holes, and intergalactic gas evolve together. Shift one stage of the timeline and adjacent stages adjust. If Webb's observations continue to support earlier stellar mass assembly at redshifts above 10, the first ripple reaches cosmic reionization. After the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. That neutral phase lasted until ultraviolet radiation from the first stars and galaxies reionized intergalactic hydrogen, stripping electrons free again. Observations of distant quasars show that reionization was largely complete by redshift 6 about 1 billion years after the Big Bang. The question has always been, what sources produced enough ionizing photons to drive that transition? If galaxies formed stars earlier and more efficiently than many models assumed, they may have contributed more strongly to reionization at earlier times. That could slightly shift the timing and duration of the process. Yet constraints from cosmic microwave background, polarization measurements, especially from the Planck Space Observatory, already limit how extended reionization could have been. So any shift must remain consistent with those data. The second ripple touches chemical enrichment. Oxygen emission lines detected in some high redshift galaxies implied that at least one generation of massive stars had already formed and exploded. If galaxies were active earlier, heavy elements would begin seeding the intergalactic medium sooner. That affects cooling processes, star formation pathways, and the emergence of complex structures. The third ripple concerns black holes. Supermassive black holes with masses above 1 billion solar masses are observed at redshifts around 6 and 7. Growing such massive objects within less than 1 billion years is already challenging. If galaxies and their dense central regions assembled earlier, that could ease some of the pressure on black hole growth models by providing longer accretion timescales. So far we know, the anomaly does not break the cosmic timeline, it compresses it. Galaxies may have transitioned from primordial gas clouds to structured, chemically enriched systems slightly faster than predicted by many pre-Webb models. That acceleration, if confirmed, influences reionization, enrichment, and black hole growth, but within boundaries set by independent cosmological measurements. Importantly, the backbone of cosmology remains intact, the expansion rate derived from supernovae, the cosmic microwave background fluctuations, the distribution of galaxies at later epochs. None of these are contradicted by Webb's findings. The shift is local to early galaxy formation physics, and that makes it both less dramatic and more precise. We are not witnessing the collapse of a model, we are observing its refinement. The universe may not have waited as long as we thought before building complex structures, but it did so according to the same gravitational rules. The timeline expands not by breaking, but by tightening our understanding of its earliest chapters. There is one final layer left. It is not about data. It is about perspective. If galaxies matured earlier than expected, the consequences do not stay local. They ripple. A galaxy forming substantial stellar mass at redshift 12 is not just an isolated data point. It is a source of ultraviolet radiation. It is a producer of heavy elements. It is a potential cradle for black holes. Move its formation earlier and you shift multiple cosmic milestones with it. Start with reionization. After the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen. That state persisted for hundreds of millions of years. Then the first luminous sources, stars and galaxies, began emitting ultraviolet photons energetic enough to ionize hydrogen again. This era, known as the epoch of reionization, unfolded roughly between redshift 6 and 10. Observations of distant quasars show that by redshift 6, most intergalactic hydrogen was already ionized. Measurements of polarization in the cosmic microwave background constrain when reionization likely began and how long it lasted. if galaxies were more numerous or more efficient at very early times, they could have contributed more ionizing photons earlier in cosmic history. That does not contradict existing constraints, but it shifts emphasis. A faster buildup of stellar mass at redshift 12 implies that ionizing radiation sources were active earlier than some models assumed. The onset of significant reionization could begin sooner, though the total optical depth measured by Planck still limits how extended that process can be. Now consider chemical enrichment. The first stars formed from nearly pure hydrogen and helium. Through nuclear fusion and supernova explosions, they produced heavier elements: oxygen, carbon, iron. Those elements enriched surrounding gas, altering cooling properties and enabling subsequent generations of stars to form differently. When Webb detects oxygen emission lines in galaxies only a few 100 million years after the Big Bang, it tells us that at least one prior generation of stars has already lived and died. If galaxies assembled quickly, enrichment cycles also accelerated. Heavy elements seeded future star formation, influenced dust production, and shaped planetary formation pathways billions of years later. There is also black hole growth. Supermassive black holes exceeding 1 billion solar masses have been observed at redshifts above 7. Their rapid growth has long posed questions. If early galaxies formed efficiently and provided dense gas reservoirs, black holes could accrete more rapidly in those environments. An earlier, faster galaxy assembly timeline may ease some tension in explaining early quasars. Though black hole growth remains its own complex problem, so far we know, Webb's observations do not overthrow cosmology. They refine the timeline of structure formation. If galaxies began assembling substantial mass earlier than expected, related processes, reionization, enrichment, black hole seeding, also begin earlier within allowed bounds. The shift is not dramatic in calendar years, it is subtle. But in a universe only 400 million years old, tens of millions of years matter. Cosmic history is compressed at early times. Small adjustments in formation onset represent significant fractions of total age. The expanding timeline is not about changing 13.8 billion years. It is about understanding how quickly the first few 100 million unfolded. And that leads to the final layer. Because beyond parameter adjustments and survey statistics lies a broader question. What does it mean that the universe may have structured itself faster than we anticipated? Not chaotically, not impossibly, just efficiently. There is one more layer to consider. When the first deep field image from the James Webb Space Telescope was released, most people saw distance. Astronomers saw timing. What unsettled them was not that galaxies existed early. That was always expected. It was that some appeared structured, luminous, and chemically active sooner than many formation models had predicted. The central anomaly has remained consistent throughout this investigation. Galaxies within the first 400–500 million years after the Big Bang appear to have assembled significant stellar mass earlier than anticipated by many pre-Webb simulations. Not impossibly early, not in violation of gravity, earlier than expected. Over the past chapters, the tension narrowed. Photometric overestimates were corrected, spectroscopy confirmed true distances, emission line contamination was accounted for, stellar population models improved, simulations were recalibrated. What remains is not a crisis, it is refinement. Dark matter halos still grow according to the same gravitational laws derived from the cosmic microwave background. The expansion history remains consistent with measurements from supernovae and baryon acoustic oscillations. THET-CDM continues to describe large-scale structure with remarkable accuracy, but within that framework, early galaxy formation physics is being tuned. Star formation efficiency at extreme redshift may have been higher in some environments. Gas accretion through dense filaments may have been more effective. Feedback may have regulated growth differently in metal-poor conditions. Rare density peaks may have contributed to more visible and more unfamiliar suggested. sharpens it. Because the universe did not behave randomly, it followed the same physical rules: gravity, thermodynamics, nuclear fusion. And within those rules, it appears to have organized matter into structured systems slightly faster than we expected. There is something quietly profound in that. For decades, our understanding of cosmic dawn relied on indirect signals, fluctuations in microwave background radiation, faint smudges in deep optical images, theoretical simulations running on supercomputers. Then a telescope positioned 1.5 million kilometers from Earth unfolded a segmented mirror and began catching photons that had traveled for more than 13 billion years. Those photons carried a message, not that our model was wrong, but that its early chapters were less hesitant than we imagined. The universe did not linger long in simplicity. Within a few 100 million years, gravity had sculpted dark matter into halos, gas had collapsed into stars, heavy elements had begun circulating, and galaxies had taken recognizable form. It grew up fast. We stand inside a scientific system that adjusts when new light arrives. No panic, no spectacle, just recalibration. The anomaly did not break cosmology. It made it more precise. And somewhere in data still arriving from Webb's detectors, in fields not yet analyzed, in spectra not yet published, the next refinement is already waiting. Not a revolution, a measurement, and we are still following it.